Okay, now let us just introduce another. So this is basically the problem is that if you draw all perpendicular bisectors, then you can clearly see that some pairs do not play a role. Okay, then P3 P5 may not play a role, or P2 P5 may not play a role. Then if you keep drawing perpendicular bisectors, try to figure out, that could be a very difficult one to do that. Okay, so assuming that you are little okay now. So can you do one more thing on the same Rangoli that you have done? Okay, you just connect 2 points, whatever P2, P4 or P1, P1 etc. Only connect the 2 points by a straight edge if they share a Voronoi edge. If they share, for example, okay, in this case if I have this case here, little bit change that. Okay. So I don't connect P1 and P3 because I don't have a Voronoi edge between P1 and P3. So I only connect P1 and P4, okay, and then P1 and P2, and then P2 and P4 as a Voronoi edge, and P3 P4 and P2 P3, but not P1 and P3. Okay. So similarly you have to figure out which all has Voronoi pairs here on that. Okay. P1 and, yeah, because that Voronoi edge is here. See, it may not be near, it may be somewhere far also, but still let us say Voronoi edge. So if you do that, what will happen? And show me the diagram. Are you all guys here? So I would strongly recommend not to use cell phones in the class. Okay, is that clear for everybody? That is highly disrespectful. Okay, the question is, you should connect 2 points if they have a Voronoi edge. For example, in this case, the P1 and P3 do not have a Voronoi edge. So you do not connect P1 and P3. Okay. So you connect all other things. If they share a Voronoi edge, you connect those 2 points, not at any other time. Okay. Is that question clear, all people? So what do you observe now? Is that diagram? I used a different color. Yeah, I just have no clue on. Okay, black has become terrible for me. Okay, it looks okay. It looks fine actually, but really. So you should connect 2 points only if they share a Voronoi edge. Okay, it can be difficult to figure out whether a pair has a Voronoi edge for this particular case, but at least in other cases it's fine. These cases are fairly clear, but diagram it's looking correct only, but I'm just trying to verify whether all properties are there. The diagram looks, but what is that you can observe on this? I think it's okay here, but explanation for me it's kind of become later. But what is that you can observe now? I think it is little nicer in either the left or the right, but not the middle one. Middle one apparently has become more complicated for me to explain, but diagram is correct actually. See, if your Voronoi diagram is correct, technically this will be correct. So if your Voronoi diagram is correct, this will be having a lot of different shapes on that. But finally, what are the shapes that you have got for this? All triangles, correct. So all of you, what is that observation that you have after doing these connections? So you only connect 2 points if they share a Voronoi edge. Okay. So what it led to finally?
Number of triangles and number of Voronoi vertex are same.
Will be same because that is how you do the process, right? Edges will be the same because for every edge, okay, I will come back to that on that. So what is that you observe?
P5 and
They do not have, in this case they do not have P phi and okay, P phi and yeah, P phi and P 3 is here. This is a Warna edge between P phi and P 3. This is P 3, this is P phi, and this is the edge between P 3 and P phi. No, P1 and P3 is here. So, you should connect P1 and P3 also. That is a good point. That is why I said this middle guy is little bit problematic, because you are having edges all over the place, which is still correct. So, you have to connect here, and then this one. P1 and P2 also has this one. Something beating here. Okay. So, this is P2 and P5 also has one. Oh. P2 and P4 as one. Wow, it is, that is why I said this is, oh, there is one more, yeah, you are right. Which between which and which? P5, P3. Right. So, what is your observation now? Not all. So, basically you are coming from Warna edge. So, whenever you do that, each Warna edge will have one edge in the triangle, if you observe carefully. So, this process that you did, so in this case, okay, if you take this case is fairly simple. So, I have this thing. So, you can see that the entire set of points is now being triangulated, not exactly like what we saw in the morning. Morning we had a input as polygon, now the input is only a set of points. So, you have to observe that carefully. So, this is this led to what? It is a triangulation again. So, this is called as the dual of Warnoy. Okay, this triangulation is called as a Delaunay triangulation. So, we can do directly also without going to Warnoy, but usually it is, these two are dual to each other, and a very extensive popular diagram, and has its hundreds of uses in all kinds of applications. So, the dual of a Warnoy diagram is called as a Delaunay triangulation. So, you have a Warnoy diagram, you pick the dual, and you can go the reverse also. How you can go the reverse? What is it? For every Warnoy edge there is a corresponding edge in the, what that? Not whatever, you should get that immediately, no, it should go to the head. What triangulation? This means this is the problem. You should get into the head quickly. So, this is called as a Delaunay triangulation. Okay. So, for every edge in a Warnoy diagram, or for every Warnoy edge, there will be a corresponding Delaunay edge. Okay. So, for example, does P1 and P3 has a Warnoy edge here? Does P1 and P3 has a Warnoy edge? So, that means what? There won't be any Delaunay edge. So, on the other hand, you can also see that there is no edge in the Delaunay triangulation between P1 and P3. That means what? There is no edge for in the Warnoy also between P1 and P3. These guys are too far off. Okay, and I'll tell you more properties. So, all of you are okay with these two diagrams, Warnoy and Delaunay? Any questions on this? This is a fundamental concept. I guess they are going to be using in a few more lectures later on. They are not going to teach you Warnoy diagram. So, Warnoy diagram and Delaunay triangulation are dual to each other. For every Warnoy edge there is a Delaunay edge. For every Warnoy polygon there is a Delaunay? No. For every polygon there is, or for every Warnoy polygon there is a Delaunay what? No. For every Warnoy edge there is a Delaunay edge. Is that right or wrong? Okay. Now, for every Warnoy polygon or a Warnoy region there is a Delaunay. That is what is not going to happen. For every Warnoy vertex there is a Delaunay. Delaunay Warnoy vertex or Delaunay vertex? Which one you want to say? See, the edge and edge only go between Voronoi and Delaunay, okay. For other cases they don't, they are exactly opposite, that is what I am trying to catch here. So, for every Voronoi edge there is a Delaunay edge, okay. If you take this black guy, there is a blue guy corresponding to that, okay. But for every Voronoi polygon there is a Delaunay Delaunay vertex, which is the point itself. So, for every polygon this back here there is a red guy which is a vertex, which is a Delaunay vertex because it lies on the Delaunay triangle, okay. This is a Delaunay vertex. So, for every Voronoi polygon or a Voronoi region there is a Delaunay vertex. So, for every Voronoi vertex there is a Delaunay triangle. We do not call it as a Delaunay polygon or a Delaunay face, that is a Delaunay triangle on that, okay. So, that means these two are dual to each other. There is an edge guy to an edge guy, but there is a vertex to a face and then face to a vertex. You can think of triangle as a face or a Voronoi polygon as a face, okay. It is also being considered, it is actually a Voronoi face also term being used, but it is be confusing if you go to higher dimensions, which I think we may not even be able to talk about it, but yeah. Mm.
Which edges to choose? We can think about like the shortest edges will start first.
Yeah, so Delaunay triangulation is also going to be useful in the nearest neighbor query on that. You can do that. In short, I just cut down your whole history geography. After that, yes, it is also for a, I think somebody Kaushik or yes about Delaunay nearest neighborhood. So, Delaunay is also can be used for the nearest neighborhood problem on that. You can draw that, yes, to start with that. Okay, now if suppose if I have drawn the wrong line, like what he wants is to have a vertical line here, okay, that means what? So, if I had a vertical line as a Voronoi edge, then what should have been edge between the Delaunay? So, instead of edge here, where will that edge be in your case? So, you wanted an edge between P1 and P3, okay. Now, if you had a corresponding one on the Delaunay, which 2 points we should connect? So, there is, if there is a Voronoi edge between P1 and P3, okay, what will be the corresponding Delaunay edge? No, that is a wrong diagram, but I want to explain the wrong phenomenon also. So, you should have a edge between P1 and P3, okay, because if he says that there is a Voronoi edge between P1 and P3, then naturally there is an edge connecting P1 and P3 which is a Delaunay edge like this. This is wrong, okay, but suppose you have drawn a wrong diagram, we have to follow that because it is a dual, we have to follow this, okay. But then what it violates, okay, let me just stand on this and then anyway delete this guy first, okay. Now, you tell me what are other observations that you can make on the Delaunay triangulation, then this will be very relevant on why this guy is wrong. See, what are other observations? See, the moment you say triangle, what are the circles that you can think of or the centers that you can think of? Circumcenter, then all you have to go to school mathematics book and take in center, circumcenter, centroid will amount to which center in a circle. That is why we have to do the schools properly. In center. So, the Voronoi vertex will be circumcenter, are all sure on that? So, Voronoi vertex is going to be a circumcenter, are all sure on that, okay, circumcenter. Suppose if we draw all the circles, what will be your observation? All the circumcircles, okay, you just draw the 2 here, okay, all possible, if you want you can draw. So, what can you say about that? There is no relation to Venn diagram on this. We could make out maybe and then become some nearest neighborhood problem, but what else you can say on that? Need not, all touch circle need not touch each other, no. No other vertex will lie on that circle, that is what I want to comment. So, all these circumcircles will be empty except those 2 points or those 3 points that contribute to that circle. So, if you draw these 2 circles, and I am trying my best, okay, something like this. So, only P1, P2, P4 will lie on these circles, but never this P3. Okay. So, I should draw with a different color. So, similar, you cannot. So, this thing like let us say P2, P3, P4, there is no way that P1 is going to lie, and you can try this in this diagram. So, if you draw a circumcircle between P1, P5 and P3, it is going to be something like this, it is going to be completely in the outward direction, there is no point it is going to lie. So, take a triangle that is inside, okay, take P2, P3, P4 or P2, P4 and P5, it becomes oval, but you can see that there is no other point will lie on this circle, only those 3 points. So, this is a beautiful property of this Delaunay triangulation called as the circumcircle. This does not happen in any triangulation that you can think of, okay, it only happens in Delaunay triangulation. Okay, so, this is called as an empty circumcircle property. Okay, suppose you had an edge between P1 and P3, what will happen in this case? Suppose you had an edge between P1 and P3, what will happen to that circumcircle? Yeah, P4 will lie inside that. So, that means this is a wrong triangulation, and this edge, that this is called as a flipping the Delaunay edge. So, when you have that, you just flip that guy. So, instead of this edge, you just put the other edge, the diagram will become correct. This is called the Delaunay, some forgot the exact name. So, this is called the flipping of a Delaunay edge, something like that. So, you can easily make a correct diagram by just a quick observation. So, if it is going to be violating that empty circumcircle rule, then you can clearly see that this edge does not have any role to play, and you just flip it to the other guy on that. The diagram will become immediately correct, instant correction that you can do. Is that clear? That is the reason why you cannot have a Voronoi edge between P1 and P3 there. That is the sole reason, because it cannot have a Delaunay edge there. So, you can go from Voronoi to Delaunay or Delaunay to Voronoi. What other observations that you can make? That is all of us are very tired already. Okay, I will give you one clue. So, now we all know convex cell. So, anything that you can think about convex cell now?
What did you ask previously?
This is what I am asking now. Bring convex cell into this relation. We talked about Voronoi diagram, we talked about Delaunay. We know something already. We also talked about Voronoi and convex cell, right? Convex cells that are the points that are inside the convex cell will only have Voronoi regions that are closed, outside will always be infinite. Now, Delaunay is also there. Anything that you can connect between Delaunay and convex cell? Too much? Huh? This is a good diagram for this. The second picture is a very nice diagram to illustrate that, except that, I mean, if you draw convex cell, what will happen now? Outermost. See, the outermost edges of the Delaunay triangulation will indeed be the convex cell. Okay, now you can go from Voronoi to Delaunay, Delaunay to convex cell, or Delaunay or convex cell to Delaunay, and then Delaunay to Voronoi. Aditya is already in deep slumber now. These three are well connected, okay, exceptionally connected on that, and this is one of the important connections people exploit when they come up with algorithms. So, in some cases algorithm for convex cell may be easier, but not necessarily the Voronoi diagram, and some cases depending on your input. We are just looking at point set now, it could be any other input, right. So, these are all beautiful connections, geometrically or algorithmically, whatever way that you want to look at it. So, the boundary of the Delaunay triangulation is indeed the convex cell. Okay. So, the boundary is a notion that you can now think of. The boundary of the Delaunay triangulation is indeed the convex cell of the entire point set. So, the Voronoi is connected to Delaunay, Delaunay is connected to convex cell, and the vice versa is also true. And this empty circumcircle property is a great one. Of course, in the Delaunay triangulation there is one more property in this event of lunch I will put you one more confusion. So, there is a property called as empty circle property, which is actually different from empty circumcircle property. People often get confused on that. Maybe we will just quickly do that, and then with more confusion we can go, because it seems to be less confusion now. Okay, so, the note down this condition. So, if we can draw a circle between 2 points and that is empty, any circle, not necessarily a diametric circle. If you can draw an empty circle between those 2 points or between any 2 points, then that edge is definitely an edge in the Delaunay triangle. If you can draw an empty circle passing through any 2 points, then those 2 points, let us say P and Q, is definitely an edge in the Delaunay triangle. This is different from circumcircle. Okay. For example, okay, you use same illustration of P1 and P3. Okay. So, this guy has become a great guy now. So, P1 and P3 if you take, so even if I take the smallest circle that I can draw with P1 and P3 is what? The diametric circle, but that is not going to be empty. So, any other circle that I draw, which is going to be, this guy is going to be a card, is definitely not going to be empty. So, there is no way that I can find an empty circle for the edge P1 and P3. Okay. So, that means there is no Delaunay edge for P1 and as a consequence there is no Voronoi edge. If and only if. If and only if. Yes, 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 both are true. Good point. This is an if and only if statement. Of course, proof is not very difficult, but I leave that task to you on that. So, if you cannot find an empty circle between 2 points, then that means it is not a Delaunay edge. This is an if and only if condition. It is a beautiful condition, which is actually very different from the circumcircle. So, in the test when I ask a question on empty circle property, they write the history and geography of empty circumcircle property. This is definitely not the question. So, this is often getting, even in general people get confused on that. There is a significant difference between a empty circle property and an, but beautiful diagrams on that. I mean, there are so many applications that I have done with this Delaunay triangulation. I do not know, we have some 20 papers on this, I think. Such a which we have not explored in my before joining at IIT. All my contributions from my students. So, thank my students. We have some 4-5 PhD theses on using Delaunay triangulation, which I never learnt till I did my postdoc. Well, you can hindsight is always a good one to look at it, but you can only learn so much, right. So, if I had known these diagrams much before, then I could have probably done maybe just a conjecture anyway on that. Okay, so any questions on this? So, there is one more guy which I will touch upon, which are called as alpha shapes and alpha L, which is again related to these guys. So, then I will touch on that also. Empty circumcircle, all Delaunay circles or circumcircles are empty. When there is an empty circle, it looks like it is an if and only if only there also. So, these two conditions are so beautiful, but empty circle is even more beautiful because it is not exactly taking 3 points, it takes only 2 points on that, and that is constituting for an edge, which is even more a pressing problem than 3 edges which constitute a triangle on that. But both are equally good. I mean, like, it's all fascinating on that. But we are only okay. I will leave out for you with some more thinking. We started off Voronoi diagram with what example? 2 points. Okay, telephone, but converted that into 2-point case on your paper, and all of you were very happy and told that it is a perpendicular bisector and so on. Okay. Now, you take 2 line segments, L1 and L2, and can you decipher the Voronoi region for L1 and Voronoi region for L2, and as a consequence can you tell me what is the Voronoi diagram? So, even a simpler thing would be, so you talked about perpendicular bisector between 2 points, right. So, what is that if you have 2 lines? It is also school mathematics only, it is not like so instead of perpendicular bisector it will be what? Angular bisector. Why are you so hesitant to tell that? It is an angular bisector is going to play a role. It is not going to be simple, that we will look at it, but if we just say 2 lines, the angular bisector will come into picture, that is all. Well, when you take 2 circles, what will happen? Point went to line, line to circle, circle to well, no, that will work only if you have constant radius circles. The circles need not be constant radii. Cylinder? Where is cylinder coming in? We are still in plane only. Okay, I will reduce this case now. Okay, we talked about 2 points, we talked about 2 lines. What is the bisector between a point and a line when the point is not lying on the line? You have to imagine your engineering drawing course in your first year. You never did?
I am not an engineer.
Okay, drawing in your elementary school. You would have definitely done that. So, what will be that? Yes, you have already done that in your school. Lot of drawings you have done in your first year engineering drawing. I am 100% sure you have done this before. Will it be a straight line? Like in a perpendicular bisector or an angular bisector, will it be a straight line? So, if you are not aware of what case I am looking at, okay, I will also put that. So, there is a point P and there is a line L. Okay, what is the bisector between these two guys? Will it be a straight line? It has to be equidistant to both P and L. Circle? It's a parabola. What is that point P in your parabola? Usually you call that as focus. What about this line L? Directrix. This is your school geometry class. That is what we use in Warnai diagram also. Okay. Now the case will get more and more complicated. Suppose if you have 2 line segments, how will you draw the Warnai diagram? Because the line segments apart from those 2 lines, I want those 2 points or end points of these line segments also to be in contention for the Warnai diagram. Okay. So, when I had 2 points, you put a perpendicular bisector, you have Warnai region of P1, Warnai region of P2. You have put 2 lines, Warnai region of L1, Warnai region of L2. But now I am saying that you should consider those endpoints also. That means there will be a Warnai region for P1 in line 1 and let us say P2 in line 1 and then Q1 in line 2 and Q2 in line 2. So, how many Warnai? Potentially you are looking at how many Warnai regions? 2 plus 4, 6 Warnai regions you are looking at. So, obviously we can go more and more. This guy is already out. So, we will discuss some of the exciting things, at least for me, if not for anybody in the afternoon on it. But think about this. We can extend it. I will show you some fascinating pictures from ERIT on this. The guy was so good. I mean, my advisor, phenomenal guy. And I think he is probably, so of course in the geometry circle he is a well known guy, one of the leading guys working in the entire. He's done lot of work on that, including trivariate and coming up with a new representation scheme from boundary rep to volumetric representation. Has been so useful in 3D printing. People are just not aware because everybody wants to do data science. That is the fundamental problem now on that. So, you just tell me how will I create Warnai diagram with data science, that is what I am telling you. So, how do I create Delaunay triangulation with the data science? And one guy did that also, very annoying to me that you convert this problem into a data science problem, which I am strictly opposed to do that as a data science. I mean, I am taking a course on data science, not that I completely do not like it or whatever. I do take a course on data science, but then converting everything as a data science problem, I strongly detest from that idea on that. And people write that also. So, I received one research paper on that, using a deep learning to do a Delaunay triangulation. We can draw that. Now, I think you are all well versed in drawing Delaunay for 10 points. So, if I give you 10 points, you can draw that. And the deep learning guy was not able to draw with 10 points, which he can do by hand. And eventually, they got a wrong result using a sophisticated technique called deep learning, and then ended up in a wrong result. Topologically, it is incorrect.
We are trying to teach the computers.
Wrong thing. Teaching somebody a wrong thing on that. I told boss, I can do it by hand. Why do you want to put me under stress by telling that I am going to do a so and so, I am the first researcher to apply a deep learning onto a Delaunay triangulation problem, and then show me a wrong result on that. So, people have become mad in wanting to use data science for all sorts of problems. They are completely mad, because everybody wants a data science on the resume. I am a data science guy. So, do not I mean, data science works for okay, you can classify a dog and a cat, which we can do by without doing data science also, isn't it? Can't you identify a difference between dog and a cat if I show you both of them? Any human can do reasonable, because you have not seen millions of cats, but deep learning will work only if you show millions of cats. You can do with 2 cats or 3 cats or even 1 cat also on that. Okay, it is not that I am against all that, but
Miracle of brain.
main is, see, brain, we all happy that it works. Either way, whatever, it works in a mad way, let us say, during that time, but it still works. But we really don't know how it works, but it's okay, right? We are happy it works, that is much more blessing. Yeah, that's how it works, okay. That is why we all think in different manner, work in different places and work in different things. Okay, so let us have some good lunch, but you think about this, we will come back and discuss some of these fascinating problems on that.